So I just want to know in general from this meeting I'll have a look at who here has already done Qiskit programming or who has not done Qiskit programming before, namely Aman and Amrit.
Yeah, we have done just a
We
little
have
bit.
done.
Okay, so
Yeah, we
you
have done a
basically
bit.
like
That's it.
created circuits and stuff like that, right? Already.
Yeah.
Fine. So when you simulated it, did you use the AI simulator or something like that to run the circuit?
Yeah, we used that AR simulator and something as matplotlib to visualize the circuits and all.
Yeah, great. So basically today I'll be talking about the quantum info module. So when you were using quantum air earlier, that basically takes measurements from the qubits and it will give you like the output of how many times 0 is measured and how many times 1 was measured, correct? No?
Yeah.
So this is the quantum info module now we're looking at. So the quantum info module, basically without measuring only, you can get information about the output state as well as certain other quantum properties of the output state. So this quantum info module, we can make quantum circuits, and based on the output states, we can measure their quantum properties. So the first step is obviously like installing dependencies. I've already installed Qiskit and Qiskit Air, but if you need to, this is how you would do it. I kept it just for completeness. So in this hands-on, what we'll be importing, first of all, we need to create quantum circuits, right? So we need to import this class called quantum circuits, but from Qiskit. So we want to import a quantum circuit class, but it's going to be from Qiskit itself, which is IBM's quantum programming language. And also, as I said, normally you would use air simulator, but here we're using quantum info, not Qiskit info. This is a typo, but quantum info. So again, I'm going to import qiskit.quantuminfo module. And I'm going to import it as like QI just so that I can use it over and over without typing quantum info every time. I'll just type QI every time. Is there any questions till this point?
No way.
Fine then. So now let's start with a very super simple basic quantum circuit where we just have a single qubit with no gates. So how to do that is very elementary, right? I'll just give my quantum circuit a name called QC and I'll assign it to this quantum circuit instance. And here, can anyone tell me what number should I put inside of this?
0.
No, because when I'm passing this parameter, it means the number of qubits in the total quantum circuit. So you can guess now it's probably 1, right?
Yeah, yeah.
Fine. So if I draw the circuit now, basically we get an output. Oh, I forgot to run the import cell. Now let me just run that first. Um, yeah, now it's run and from Qiskit import quantum circuit. Then yeah, now I do the quantum circuit. So we see here, yes, now there's a single qubit in this quantum circuit without any gates applied. And as you might have already seen, like you can apply matplotlib to make it look in a graphical format, not in a text format. So I can just do quantum circuit.draw in matplotlib or MPL format. And we see over here that now we just have a qubit whose name is Q, and it's just like a line. There's no gates applied like X or anything. So now let's see how we can obtain its state vector, like the ket 0 basically, right? Because in Qiskit, all the qubits start off as ket 0. How can we obtain the state vector using quantum info? Usually I'm going to use this variable name ket psi because that's what they usually do in quantum mechanics. And I'm going to assign it to quantum info, which was qi dot state vector function. And I'm going to pass the circuit, which is QC, as its parameter. So what this will do is it will take this quantum circuit and return the state vector corresponding to the qubit in its output state. And let me try printing out this psi. And what we see here, it's basically this state vector object, which is an array. And the first element is the probability amplitude of 0, which is 1. This 0j is basically the imaginary part, so there's no imaginary part. We can see 1.0 is the amplitude for 0, and 0 is the amplitude for 1. So this is the state 0. And we can even make this look proper in Dirac notation by using, instead of print function, we take psi and we can do dot draw in the output format using latex. LaTeX is basically like a mathematical rendering language. And when we print it out, we can see we get 0. We should. Yeah, so basically this is the quantum state psi. And we can even you visualize it on the block sphere using quantum info by doing the same thing, get psi and draw it. But this time we're not using LaTeX because that's text. Now we can use the block representation. The block, so we see in the block sphere now, we obtain the visual representation of ket 0 because the state vector is pointing at the north pole, which is the ket 0 state. Are there any questions until this point?
No way.
Fine then. So now we just took a plain simple qubit. Now let's apply the X gate onto that qubit and see if it adds up. So as we know the X gate, when we apply it to state 0, we should get a state 1, right? And we can also verify this mathematically. So the X gate or any gate in general in quantum computing is represented by a matrix. And specifically the X gate matrix will be 0, 1 and 1, 0. When we apply this X onto the state 0, it's the same as multiplying this matrix 0, 1, 1, 0 with 0, which is 1, 0. This is the state vector corresponding to 0. And when we do that, it's basically 0 into 1 plus 1 into 0, which is 0, and 1 into 1 plus 0 into 0, which is 1, which is nothing but the state 1. So now let's actually just run the circuit and see if it verifies that way. So onto the quantum circuit, we want to apply a gate called the X gate on qubit 0. And can anyone tell me why we took 0 over here and not 1? Because we're applying it on the first qubit, right? Does anyone know why we put 1 over here and not 0? I mean, why we put 0 instead of 1?
The first, it's maybe the indexing part.
Correct, yeah. Where Qiskit basically always uses indexing for the qubits starting from 0, like how arrays are. Like it starts with Q0, then Q1, then so on, instead of Q1. So that's why we choose the X gate on 0. And followed by this, I want to just draw it and we'll see how it looks using matplotlib. Yeah, this is correct, right? We have a single qubit and we apply the X gate. Now using the same method, I'm just gonna get the state vector and show you in Dirac notation and on the block sphere. So I'm gonna take psi, I'm gonna assign it to quantum info dot state vector on the quantum circuit, and I'm going to draw it using first LaTeX, which gives us the Dirac notation. We see ket1, right? Is this correct? Yes. Then we check with the block sphere, which is the same step. So psi dot draw using the block sphere representation. Now we get ket1. So we've also seen that it works once we even applying gates after applying X gates. Now let's go additionally for the Hadamard gate before we move on to like some more features. So we'll just simply apply the Hadamard gate, which is H onto qubit 0 and draw it again just to see the final circuit. We see this is the circuit. After applying the X gate, which we did previously, now we simply apply the Hadamard gate. And the same thing I will use to find the state vector. I'll just copy paste the code so it's faster. I'll copy paste this code. Now we have the state vector. We're getting this state now. We're getting an equal superposition state of 0 and 1. Now why is this equal superposition? Because we can see the coefficients for 0 are equal to the coefficients of 1. And that basically means there's a 50% probability that we measure 0 and a 50% probability of measuring 1. Before I prove this mathematically, I'll also just show this on the block sphere as well. So I'm going to draw this using the block sphere representation. We see it's coming in this place between 0 and 1. So there's an equal probability. But now let me actually just prove it mathematically why exactly we're getting this state. So we saw initially that we applied the x to 0 and we got this state 0, 1. Now we need to apply the Hadamard gate, whose matrix is 1 upon root 2 into 1, 1 minus 1, 1. Now let's try applying this gate onto the new state, which is 0, 1. So when we do that, we get 1 by root 2 remains as it is.
Archit,
Yes, sir.
Sir,
I think
maybe,
matrix is 1 minus 1, not minus 1, 1.
yeah,
Oh,
1,
yes,
1,
sorry.
1 minus 1.
Sorry.
Uh,
This should be minus 1. Thank you for correcting me. So we see the top row, it's 1 into 0 plus 1 into 1 basically, which is 1. And then 1 into 0 plus minus 1 into 1, which is minus 1. So basically what we're getting is this equal superposition state, which is like 1 upon root 2 into, if I write in Dirac notation, it's ket 0, but minus of ket 1. Because of the minus 1, we're putting minus. So it's an equal superposition state, but this minus just represents that the phase is inverted between the 0 and the 1, which is why we see the vector going in the backward direction instead of towards us, which would be the plus state. Are there any questions up to now on why exactly we're getting this particular state vector? Fine, I'll assume there are no questions then. Now, I told you there's an equal probability now of measuring 0 and 1. Now, I'm going to justify that by using, again, quantum information through which I can get the probabilities as well. So I'm going to store the probabilities using a variable called probabilities. And it's going to be the state vector dot probabilities, which is also a function of the, what do you call it, quantum info module. And I can print out this probabilities. And is this not correct? We're getting 0.5 probability for measuring 0 and 0.5 probability for measuring 1. Now let's
Yeah,
look into something interesting. So when we were doing air simulator measurements, we had to actually do a quantum circuit dot measure, right? Is that correct?
Yes.
Otherwise, yeah, we cannot get the counts. So let's see what happens in the quantum info module, because we were measuring quantum properties. Let's see what happens if we try to measure this. So if we do quantum circuit dot measure all, this is the short form of just measuring all the qubits that are in our circuit without explicitly mentioning. And if we draw this vector, draw the circuit, we see, yeah, we've done the gates and now we've measured it onto some classical register. Now let's try to get the state vector. I'll just copy paste the code again. Get the state vector and draw it, and let's see what happens now. I'm going to just run this code. Oof, I've got an error over here. And let's scroll down. Let's see what error it is. It says cannot apply instruction with classical bits measure. So I'm just curious. I'm going to come to the meeting here. Is there any guesses as to why there's an error coming over here and it's not just working as it is?
because we have measured it, so now it's a classical bit.
Yeah, in a sense, it's kind of like that. Basically, quantum info, like I said, it measures the quantum properties of the circuit itself. So once you do measurement, its quantum property is lost in some way because of like collapsing of the superposition. Like formally, if I had to say it, if you know, I'd say it's a globally not a mixed. It's a globally mixed state, not a globally pure state. If you know what it is, it's fine. If you don't know, ignore what I said. So yeah, like I said, we see that it only helps in theoretically analyzing the quantum properties, but the measurement operation destroys these quantum properties. Therefore, we have to use like simulators like Air Simulator or Qiskit IBM Runtime if we want to actually get deal output values. But this is quite useful when we're like looking at quantum algorithms when we're theoretically treating the circuit. But one side note, there is a way that we can simulate the circuit anyways and get the counts using this, but it's not recommendation because it's not recommended due to performance issues, and we'll actually do this quite soon. So now let's move on to multi-qubit circuits. So initially we saw single qubit circuits. Now we'll go to like a 2-qubit circuit. So let's see what this says. It wants us to create a quantum circuit with 2 qubits and apply the H gate to both qubits. So can anyone in the teams quickly just tell me how will I create the circuit now?
We'll use the quantum circuit class and pass two arguments.
Okay, and what am I going to pass as the argument?
We'll pass two because we need two
Yeah,
qubits.
correct. And I'm going to call it QC again. So this is now my quantum circuit. And what does it say? What gates do I want to apply to which qubits?
Hard gate to both the qubits so that they become entangled.
Correct. So how will I do it? Syntactics, how will I write the code now?
QC.H
Okay,
to the first qubit,
so
0.
what? Should I put 1? Correct, it's 0. And here also, what will I put?
QC.H1.
Yeah, so this will work. Let's try to just draw it using matplotlib. Yeah, basically we've gotten Q0 and Q1 both Hadamard gate. I'm just gonna add like an interesting point here. You could write it in two separate statements, but you can also do it like this. You can just pass a list of what qubits you want directly into this Hadamard thing. So if you pass this list, it will apply it both on Q0 and Q1. If I run it again, you'll see the same thing happens. But this is also completely valid. But usually when we're like using for loops and stuff in like large quantum circuits, we'd usually pass a list itself.
Okay.
Fine, now same thing, state vector. I'm going to take psi and I'm going to assign quantum information dot state vector on this quantum circuit, and I'm going to print out psi using Dirac notation, which is draw it using LaTeX. So this is the state we get. So it's 1 by 2 into 0, 0, 0, 1, 1, 0, and 1, 1. So in a sense, fundamentally what it's saying is Q0 and Q1, when we measure them, there's an equal probability that we get 0, 0, 0, 1, 1, 0, and 1, 1. And this is called an equal superposition state, which is a trademark of the Hadamard gate. Now let's verify mathematically whether this actually is the state that we get when we apply a Hadamard gate to 2-qubit system. So I'm going to just reconnect here and I'm going to clear this board. Fine. So we had I'm just going to quickly draw the circuit in mini form over here. So we had a Hadamard here and a Hadamard here. So how do we represent multi-qubit systems? Can anyone in the like group tell me what is the mathematical way we represent more than one qubits?
Oh. We add the matrices.
That's if we want to do multiple matrices together, multiple operations together. But let's say initially at this point, let's say this is like phi 1 or something. Over here, we say the first qubit Q0 will be in ket 0, and the second qubit Q1 will be
Tensor
also
product.
in ket 0. Correct. Yes, you said the correct word. You combine these two using a mathematical operator called the tensor product. So how do we do that? Q1, Q0 is in state 0, right? So we write it like this, 1, 0. And Q1 is also in state 0, which we write as 1, 0. And in between these, we can combine them using the tensor product operation. And how do we actually compute this tensor product? Is we take the pairwise combination of all of the terms. Meaning, for this term 1, we'll multiply it with each and every term of this to get a separate value. So what is 1 into 1? It's 1. What is 1 into 0? It's 0. Now if you consider the second term 0, 0 times 1 is 0, and 0 times 0 is also 0. So this is what state we got. This is how we write the vector, and basically what it means is 0 and 0, and we can write it in a single way using Dirac notation like this, ket 0, 0. Are there any doubts for what I've done with this tensor product stuff?
No, Bhaiya.
Fine then. Now we have to look at what operation are we applying. We're applying the Hadamard gate to the first and also to the second. So on its own, the Hadamard is like this, like we said earlier, 1 by root 2 into 1, 1, 1 minus 1. But now how will I write the Hadamard on one and also Hadamard on the second qubit? It's a similar concept, just like tell me what we'll use, what mathematical construct will we use for this?
Tensor product itself.
Yeah, correct, absolutely. So we're going to use the tensor product when we're combining both the qubits operations as well. So basically now we're getting a 2-qubit operation from 2 single qubit operations Hadamards. And how we do that now, it's the same concept. So we take 1 by root 2 into 1, 1, 1 minus 1. And we're tensor producting it with again 1 by root 2 into 1, 1, 1 minus 1. So now it's a bit longer, but it's the same idea. So I'm just going to take 1 by root 2 and 1 into 1 by root 2 outside so that I don't have to worry about it. It's going to become 1 by 2. But now looking at the actual values, for this first value 1, I have to multiply it pairwise with each and every single term here. So what am I going to get as the first 4 values? 1 into 1 is 1. I'll just write it over here. So 1 into 1 is 1. Then 1 into 1 again, 1, 1 minus 1. So this is for this top leftmost element. Now for this top rightmost element, it's the same thing, right? 1 into 1, 1, 1 minus 1. So I'll get 1, 1, 1 minus 1. Again, for the bottom left element, if I take this color, again it's gonna be 1, 1, 1, minus 1. I'm just gonna quickly write that. But for this last element, can anyone tell me what my entries are gonna be when I multiply each of these terms?
-1, -1, -1, 1.
Correct. So this is our final state, -1, -1, -1, 1. So now this is basically what? This is a large representation of the Hadamard applied, two Hadamards, like a 2-qubit Hadamard gate applied on these 2 qubits. So now let's actually apply it on these 2 qubit state. The 2 qubit state was what? 0, 0, right? Which is represented by this vector, 1, 0, 0, 0. So I'm gonna write that over here. I'm gonna apply it on the gates on the state 1, 0, 0, 0. Now this is a simple matter multiplication. It's 1 into 1 plus these are all 0 terms, right? So I'm just gonna neglect all of these terms in a way. This is like a shortcut I'm just doing so that I can just get the final answer quickly. So I get 1 by 2 into 1 times of 1 is 1. Then 1 times of 1 is 1. Then 1 times of 1 and 1 times of 1. So I'm getting this. What does this mean? I'm gonna write it back in Dirac notation so we can really understand. It's 1 by 2 into the first state will be what? Ket what? Can someone tell me? Ket question mark. What is this question mark?
0,
Get
0.
0.
Yeah, it's 0, 0. Because 0 would be for a single qubit, and a single qubit will be a two-dimensional vector because it can be it'll have an amplitude for 0 and 1. But this is the four-dimensional vector for a 2-qubit system. So the first is 0, 0, not just 0. And what will be this term? Plus?
0, 1.
Okay. And then I think you can quickly tell me the other two.
1, 0, 1, 1.
Absolutely perfect. So this is finally what we get from our circuit. 1 by 2 into this 4 combinations of these 2 qubits. Is this exactly not what this simulator has told us? Correct, no? So now let me
Yes.
apply the block sphere visualization as well. So I'm going to take psi, and I'm going to draw it using this block representation. Now we can see basically, yeah, so qubit 0 and qubit 1, they're both in this equal state between 0 and 1. That's why when we measure this, we get this equal position between 0, 0, 0, 1, 1, 0, and 1, 1. And let's also verify the probabilities just like how we did. So like the reason it's 1 by 2 is because we get the probabilities by squaring the amplitudes, right? So 1 by 2 square should give us 1 by 4 or 0.25 probability for all of these 4 cases. And let's do that quickly. So let's say probabilities is equal to, like we take this state vector psi and we apply the probabilities function. And let's print out these probabilities as well. Yeah, correct, right? Why is this size of 4 instead of before when we were having a size of 2? Can anyone tell me this? I'll repeat the question. Initially, we were having this circuit, and when we measured it, we're getting a vector of size 2 for the probabilities of the different measurements. Now, when we're taking this new circuit, we're getting a vector of size 4. Can anyone tell me why we're not getting size 2 of these probabilities?
So there are equal probability. There are 4 equal probabilities of
Yeah, in
that.
general, that's the idea. Yeah.
Yeah.
There are 4
Basically, in the
states
first.
in which the vector can be present.
Sorry.
Yeah, the vector can collapse. It can collapse in 4 possible states. So that's why we're getting 4 probabilities.
Yeah, correct. So basically, in the first case, it was 1 qubit. So there were 2 possible states, 0 and 1. Now we had a double qubit. So for each of the 0 or 1 of the first qubit, there could have also been a 0 or 1 of the second qubit. So there are 2 times 2 or 4 possible combinations. Fine. Now, I told you a bit earlier, we can actually anyway simulate the circuits using runs without Qiskit Air inside Qiskit Info itself. But it's not recommended because Qiskit Air is air simulator is optimized to run these things efficiently, and it's also implemented in C/C++. Whereas this quantum info uses linear algebra, which is a bit slower in implementation. But anyway, just for completeness, I'll show you how to do it. So we can get the counts and how many times you measure either 0, 0, 0, 1, 1, 0, or 1, 1 by taking this quantum info and by taking the state psi and running sample counts with some number of shots. And I can print out the counts. So what does this mean? I'm basically taking this state vector psi, which is this equal probability state, and I'm sampling the circuit 100 times, and I'm storing how many times I'm getting 0, 0, which is 27 times, 0, 1, which is 25 times, 1, 0, which is 27 times, and 1, 1, which is 21 times. And if I run this again, I'm getting a different value. Can anyone tell me why I'm not getting the same values every time I run this?
Because those are only probabilities.
Yeah,
It will
correct.
change
It's
with
like,
every iteration.
yes, it's like saying like if I have a coin, there's technically theoretically 50% chance of me getting heads, but if I flip it 10 times, I might get it 6 or 7 times just by like empirical luck. So this is what it's meant over here. If I increase it to 1,000 times, statistically they'll be closer to like 1/4. Like 250 is quite close over here. So that's why the number of shots also matters. Fine? Is there any doubt up to this point?
No.
Fine then. So we got the counts here, right? We can easily see this on a graph using a Qiskit visualization package. So I'll just do one more import. So from qiskit.visualization, I'm going to import a function called plot histogram. And when I use this plot histogram function and I pass these counts that I got, I basically see it's just a visualization way of doing it. And almost everyone uses this function, even in research also, to get the number of counts. Now you must be saying, okay, fine, I got the number of counts, but what if I want the actual order? Like the first time I ran this out of 1,000, which one did I get? The second time, which one did I get? Third time. You can also do that. And you can do that using a similar function. So I'm going to store these samples using a function called sample memory. And I pass the number of shots. I'm not going to put 1,000 because it will be a huge thing to print out. I'll just put 10 shots in this case. And I'll print out what samples I got. So what it's doing basically, first time it measured 0, 0, then the second shot it measured 0, 0, then 0, 1, then 1, 0. So for 10 times it's basically printing the memory of what samples it got. That's what this is used for. Anyway, this is not very useful in general unless you're doing something very specific. So now let's check out some more other interesting quantum properties. Because what we've seen so far is the actual state vectors and the actual state factors in Dirac as well as block form, as well as what probabilities they are, and verifying them mathematically. But let's check some other quantum properties. And I don't expect you to completely understand all of these unless you've like done a bit of work into this. But we'll kind of go slowly and see if we can get the gist of it. So one thing is expectation value of a state vector with respect to an observable. So I know that's a huge mouthful. So let's go understand the terms a bit. So first of all, observable. In quantum mechanics, an observable is basically some kind of physically measurable property of a quantum system. For example, its momentum or its total energy, etc. And this is represented mathematically simply by a matrix, and specifically a Hermitian matrix. A Hermitian matrix just means that its conjugate transpose is equal to itself. So like if you take a matrix O and you do its conjugate transpose, you get O itself. That's what it is. But fundamentally, it's some observable, as the word suggests, it's some observable or measurable uh, feature of a quantum state. And when I say a quantum state, it's obviously going to be described by a state vector, which I say ket psi. Now, when I measure this observable quantity on the state vector, due to its probabilistic nature, I can get different values at different instances of time or at different runs of the circuit. So because of that, I need to calculate something called an expectation value. So that is on average, what do you expect? And if I take a very basic example of this, if I'm flipping a coin and there's a 50% chance of head and 50% of chance of tails, and I say like my observable or like something that I can observe is the number of heads. So on average, my expectation value for how much I can observe the number of heads is going to be 0.5. Why? Because if I flip a tail, it's going to be 0 heads. And if I flip a heads, it's going to be 1 heads. And on average, the expectation value for how many heads I'm going to get will be 0.5. Anyway, this needs somewhat care taken when explaining, but in general, I'm just showing how to calculate observables now using Qiskit. So don't worry about what observable this is. Just trust me that this is some some observable that you can create, and I can display it in latex format. And like I said, it's a matrix. So it's a two qubit observable. So it's gonna be a 4x4 matrix. Now using this observable, I can calculate the expectation value using Qiskit Air as well. Qiskit info module, and I do it like this. I store a variable called expectation value, and I'm going to assign it to quantum information. So I'm going to take a psi and I'm going to find the expectation value with respect to the observable O, right? And let me print out my expectation value. So what we see is this O observable, whatever it is, don't worry about what exactly you're observing or measuring here. This observable, which is represented by this matrix, on average, from this quantum state, we're expecting it's gonna have this 0.1 value. And mathematically, we can check it by performing this sandwiched inner product between the state and the observable O. But I'm not going to go into it because it's beyond the scope. I just wanted to show that there are useful things beyond just simulation that this Qiskit quantum information package can do. And another thing is the density matrix. If you know what that is, it's great. But if you don't also, I really don't expect you to understand what it is at this point. I'm just gonna, I just kept this in case you're
Archit,
interested. Yes, sir?
Archit, can you print your psi vector here where you are observing the expectation value? I just want to check it once.
Oh, the side, it's this one. It's the equal super. It's this one, sir.
Which one? Oh, you haven't changed still that. Okay, fine, fine.
Actually, fine. At the end of the session, I'll actually just do the math anyways, and we'll check it out. That fine. We can do that. We can prove that it's equal to 0.1. This 002 thing is just a rounding error, and this j is just the imaginary component. And actually, if it's an observable, the imaginary component should always be 0. But let's not get into that. Now, another thing is we can use it to compute a density matrix. Basically, if you're interested, you can go into this. It's related to something called, you can read about mixed states and pure states. But for now, I'm just gonna like skip through the explanation, and I'm just gonna basically just tell you that you can use it to compute something useful called a density matrix. I'm gonna just leave this for you to study on your own once I share this code if you're interested. But now going on to something that is actually more interesting that I use almost all the time. You can use this quantum info package to find a unitary matrix for an entire circuit. So you just pass the quantum circuit you're getting, and it will give you the whole unitary matrix that represents the transformation. So like, let's just take a step back. For those of you who don't know, all quantum operations have to be in the form of a unitary matrix. And like we said, even if it's about multi-qubit systems and multi-qubit gates, they're also unitary matrices, but we just take the tensor product to get the final resulting unitary matrix. So let's just check what the unitary matrix for our circuit was where we applied two Hadamard's. So I'm going to call it U, which is our unitary. I'm going to use quantum information dot operator. An operator is almost synonymous with the word unitary because a unitary is performing some operation on a qubit. It's like semantically just the same. And I can even print out this unitary U. So what am I seeing over here? It's a 4x4 matrix. Does this make sense to you guys? Because a 4x4 matrix will be for a 2 qubit system. And I can see that it's 0.5, forget these J terms. These J terms are related to imaginary components. But basically it's 0.5, 0.5, 0.5 minus 0.5. Does anyone recognize this thing, this 0.5 minus 0.5 thing that we did anywhere earlier? Can anyone tell
It's
me?
a tensor product of Hadamard with Hadamard.
Exactly. Which is basically what we computed earlier, right? Over here. This tensor product of Hadamard with Hadamard. One sec. Yeah, this thing.
Ar-
1 by 2
Archit,
into
you
this
can
thing.
print the LaTeX format. That would be very
Yeah,
clear
yeah.
actually.
Yeah, so I was gonna do that. So when we display in LaTeX, it's the same thing how we did with Sci. Can someone guess how we're gonna print this in LaTeX? Anyone in the teams how we did earlier? Can anyone guess how what code we're gonna write to print it in LaTeX? Huh?
Sci.draw and will pass a latex as the argument.
Correct. So when we get this is basically 1 by 2 into, if I take 1 by 2 out, it's 1 by 2 into 1, 1, 1, minus 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1, 1, which is basically the Hadamard that we applied. Correct, right? So it's told us the unitary for this entire huge circuit without us doing any calculation. But we did calculation on this just to like prove it's correct. So this is actually very useful and we use it quite often when we're implementing quantum circuits or algorithms where the circuit is huge in nature and very complex and we want to verify whether this unitary is like the same as what we expect it to be. So are there any doubts until now on what we're doing and why we're doing anything?
No, bhaiya, everything's clear.
Fine then. So if it's clear, I just want to move on to like, so we just explored everything. This is almost everything you can find in the quantum info package. I tried to put into this notebook. Now let's do a small exercise where we try to like merge our knowledge, apply it to a Bell state. And also I've left a homework problem for those who are interested in like practicing a bit more and trying some new stuff. Cool? So let's understand the question, the exercise question, which is the Bell state. So it says to create a circuit to maximally entangled Bell state, which is this state, which is ket phi plus is 1 by root 2 ket 0 0 plus ket 1 1. And like non-mathematically, what this means is there's an equal probability of measuring 0 0 and 0 1 for both in a 2-qubit system. Because we're understanding that there are 2 qubits because of the ket, there are two numbers. But there is no probability of measuring 0, 1 and 1, 0 like we earlier had in the Hadamard when we applied two Hadamards. Correct, right? So we need to create this circuit and then after that it's asking us use this Qiskit info module. It's actually quantum info. I'll actually fix this typo. It should be quantum info module and we need to check the following. Find the output state vector and display it in Dirac and Bloch-sphere notation and measure the probabilities for each state and visualize it in a histogram as well as find the unitary matrix of the circuit. So first step is to actually create the Bell state circuit. So what I'm going to quickly do is write up the code and then we'll understand how we're doing it. So we're going to create a quantum circuit called quantum circuit. And can anyone tell me what number should be in here and why? How many qubits do we have and why?
2 qubits.
Yeah. And why is that?
Because what we have here is a tensor product of 2
Yeah,
qubits
correct.
with probability equal.
Yeah, basically. So we have 2 qubits here. And basically when we create a Bell state, it's a very famous circuit. So the idea is you apply Hadamard on the first qubit. So there's an equal property of 0 and 1. And conditionally on the value of the first qubit, you might apply a NOT gate on the second qubit. And we write that using a C naught or a conditional NOT gate. X is like a NOT gate basically. And the first qubit is the control. First is because 0 is the first one in Qiskit and 1 is the second qubit. And if I just draw this so you can understand what exactly we're doing here. This is the circuit. So when I apply Hadamard gate to Q0, followed by a control NOT to between Q0 and Q1, I get this this state, which is the Bell state. I'm going to leave this as an exercise to you to verify that this actually is the case. And we've actually also done this in our workshop as well as previous lectures. So you can refer to that if you're having difficulty. Now, what's the next step? Finding the output state vector. I'm actually going to ask for your guys' help now. Can you tell me how can I get the output state vector? Just tell me the code quickly. Like I'm going to call it psi. What should I assign it to?
UI dot state vector.
Yeah, qi dot state vector. And what is the what am I going to pass as the parameter to the function?
The circuit.
QC.
Correct. Quantum circuit. Now I want to display in LaTeX. That's the first thing they ask. So how am I going to do it? You guys can keep yourself unmuted. This part will be kind of quick and we'll get it done with if you understood it well.
QC dot draw with latex.
Fine. So now we've gotten the state. Root 2 by 2 is what? Nothing but 1 by root 2, right? So it's 1 by root 2 into 0, 0 plus 1, 1. And you can also verify that mathematically, but I'm going to trust that quantum information is correct for now. Now next, what does it want? Block square. Can you tell me how to do that quickly?
The same. We'll pass block as the argument.
Fine. Now, this is very interesting. Can anyone tell me what happened to the arrows over here? Why are there no arrows? Can anyone guess? Why are there no arrows at all? Like before, fine, you would put like maybe if it's Hadamard, it'll be here. If it's Hadamard, it'll be there or something. But why is there absolutely no arrows? Has Qiskit messed up, or is there something more fundamental over here?
The qubits are entangled.
Correct. So what Asmita is trying to say is when we have entangled qubits, the measurement of 0 and 1 are correlated. Measurement of qubits 0 and 1 are correlated. Before, when we had the two Hadamards, like let me go back to this circuit, way back over here. When we had these two Hadamards, it's like similar to saying like Q0 is one coin flip and Q1 is another coin flip. It's the result of Q0's measurement has nothing to do with Q1. There's no correlation between the results. And that's why we also got a completely equal state of 0, 0, 0, 1, 1, 0, 1, 1. But if we go back to this circuit, this is a Bell state. And what we're seeing is there's a 50% chance of 0, 0 and 1, 1. Or in other words, both the qubits values will always be measured as the same. So there is a correlation between them. And I cannot distinguish that this is one qubit and this is another qubit. A very layman example of this was if I have two gloves and I shuffle them together, like a right glove and a left glove, and I shuffle them and I give you a glove, there's a 50% chance you might get a right glove. But if you do get a right glove, you know that my glove is a left glove. So our results are correlated. Therefore, I cannot even say that qubit 0 and qubit 1 are different entities. Fundamentally, at the quantum mechanical level, their wave functions are like one. Their wave functions are merged. They're not as distinct entities. Physically, they're also not distinct entities at that point. That is why I cannot say that this qubit has this state and this qubit has this state. They are both entangled. And this is why there's no output for this.
Can I ask something?
Yeah, sure.
Yeah, so does this mean that when the first qubit appears, so then the block sphere representation of the second qubit also appears?
Okay, well, the thing is qubit 0 and Q1 exist beforehand, even before applying anything. At that point, they're in 0, 0, right? It's not
Yeah.
like qubit 1 appears only once I do this operation. And another thing is you said block sphere, right? Block sphere is not really a qubit. A qubit is not an arrow or anything. A qubit depends on the physical implementation. It could be an atom.
I'm
It
talking
could
about the
be,
representation.
yeah, qubit is just block sphere is just a representation mathematically. Actually, what this would be, if you're talking about mathematically, it's a six-dimensional entity that you can't visualize in your head. That's why you can't even print it over here. why it's a 6-dimensional is because this 0, 0 is like two dimensions plus a phase dimension, and this 1, 1 also corresponds to another 2 plus a phase dimension. Then then you might ask also.
Archit, I just
Yeah.
want to add this.
Thank
This
you.
is whatever Archit told. This is the basic problem. So as far as we have something three-dimensional, we can represent on the block sphere. But if we have multi-qubit states, they are not possible to represent on the block sphere. So block sphere is just to make the basic understanding, and it comes due to the spin system basically. So if you have entangled state, so block sphere is not sufficient to represent that. Even if we go up also, that same problem is there. So only two state you can represent as far as qubit are independent to each other.
Yes, sir.
So multi-qubit system block sphere cannot give you the representation because dimension become like increase.
Does that calculate out?
Is that answer your question, Amrit?
Yeah. Yes, sir.
Okay. Yeah.
Yeah. Fine then, I'll just continue. So basically the second thing so we're saying is just like, because these measurements are independent, I don't treat them as a 2-qubit system. I treat them as separate 1-qubit systems. So in this, like, this is qubit 0 and qubit 1. Yeah. Whereas here it was like they're dependent, so we can't represent it in 3D. Fine. Next part of the question, measurement probabilities. How do we find that?
Just one more thing I want to mention here, if maybe new student is not aware. When we talk about the entangled state, they cannot represent as a tensor product of two qubit. So if you go up, we'll discuss the tensor product, Archit. You can go to notebook only. That's fine.
Oh, I
Where
didn't
you apply
mention tensor
the
product anywhere, so.
So when you have this 200 qubit here, so uh, when you doing this tensor product, you have four states. But if you see the Bell state, there is no 0, 1 and 1, 0 state in that. So by no means you cannot represent the entangled state and what is known as the Bell state by tensor product. So this is also one more fundamental difference, and that's why also its representation become hard. But for quantum information, entangled states are more important. Fine, Ajit, you can go.
Okay, sir. Yeah, so the next part was find the measurement probabilities. Does anyone remember how we did it before? How will we find the probabilities? Just keep yourself unmuted and we'll blitz this through. Anyone in the
Psi dot
meeting?
probabilities,
Okay, psi dot probabilities.
and then you print probs.
Yeah, sure. Perfect. So what are we getting here? Can anyone tell me why there's 0 here, 0 here, why there's 0.5 here, 0.5? What does this mean?
Because their amplitudes are zero right now, so they won't have a probability.
Okay, yeah. So this is 0. This was state 0, 0, then 0, 1, 1, 0, and 1, 1. And we're seeing that only 0, 0 and 1, 1 can be measured. And that's also part of why we cannot divide using tensor product, because there's no mathematical way that we can represent these as two separate entities. Fine, we found the measurement properties. Now it's saying basically like simulate and visualize. Simulate and visualize. So how do we do simulations within this quantum information? Someone tell me. I'll start off with a hint. Yeah. What's the next step?
Sample counter.
Okay, yeah, sample counts of
QC.
no, because actually how it should be, I'm taking the state vector and sampling it, right? So I should take slash psi dot sample counts. And what should I mention here? When we are sampling, what was important?
Oh, the
The
shots.
shots.
Correct. How many shots? Okay, I'll take 100 shots, let's say. And let's print out these counts to see if we're actually getting something. Nice. So basically we're seeing what? There's approximately 50 of them, 50% of like 0, 0, 50% 1, 1. And absolutely none of them are coming as 0, 1 or 1, 0, which is an important thing to note. Because it's a Bell state. Otherwise there would be a probability. Now let's visualize this. We already saw this. I'm not going to waste time. Plot histograms. Plot histogram using these counts. And yeah, we just see approximately 50-50. Even if I run this again, I'll get different values. And I can get something closer to 50-50 maybe. Okay. The last part of the question was unitary matrix. Can someone tell me how to find the unitary corresponding to this entire matrix? Sorry, unitary matrix corresponding to the circuit, sorry. How am I going to do it?
Operator.
Correct. So what will I put? Operator. Of? Does anyone remember? Well, we're finding an operator for what exactly? Corresponding to what? Anybody can unmute if they know. Fine, then I'll just say it. Basically, we're finding the operator which corresponds to a specific quantum circuit, right? That's why I have to explicitly tell it that you have to find the operator for this quantum circuit. And this also matters. What if I have like 2, 3 quantum circuits? Which operator will you find it for? That's why you have to specify which quantum circuit you have to find the operator for. And also this has to just be QI dot because it's within the quantum info package. Fine. Now let's try to draw it using LaTeX. And we see we get this. I want you to like verify this on your own. How will you verify this? Apply this, apply Hadamard to Q0 followed by C0 between Q0 and Q1, like based on the matrix. And one thing I'll mention if you're trying this at home, H, and at this point you should apply an identity operator simultaneously because you have to apply a 2-qubit operator. So identity operator basically does nothing to the qubit. So first you apply an Hadamard tensor product with an identity. Then you apply a C0, which anyway is a 2-qubit operator. You don't need to tensor product with anything. After that, I'm sure you will be getting this and you can verify that on your own. Fine then, so basically this is one of the main utility of the quantum info package. And I've left a little homework, which is not very difficult and it's not a long stretch from what we've already done. It's related to something called a GHC state. And what is a GHC state? Fundamentally, it's basically a generalized version of our Bell state, which has n qubits. Because when we saw our Bell states are basically 2-qubit completely entangled states. Completely entangled means there's a complete correlation between the 0 and 1 measurements. Because they're either the same, they're always the same, whether they're 0 or 1. Now a generalization to n qubits would be, well, if there are three qubits, all of them will either be 0 or all of them will be either 1. Or if there are 5 qubits, a 5-qubit GHC state would be 5 zeros or 5 1. So in general, an n-qubit GHC state would have n zeros altogether and n ones altogether, each of which have an equal probability of being measured, which is related to 1 by root 2. Because when I square it, I get a 0.5% probability of measuring them. So now what I want you to do, take a Python function that takes an input as an n, which represents the number of qubits in the state on the GHZ gate, GHZ state, sorry. And I want you to create a circuit which represents this GHZ state. And it's going to be quite similar to our Bell state. We just apply Hadamard only to the first qubit. And from the first qubit to all the successive qubits, we're going to apply C0 gates. That's just a hint, and you can try this on your own. And I want you to use quantum info module to print out the resultant state vector in Dirac and the same stuff we did, the measurement probabilities as well as the unitary matrix. And for those of you who have already like know the basics well and have also reached an intermediate level, here's an additional question for you, which you can try out. If you know how to run actual jobs on real IBM quantum hardware, I want you to try running an 8-qubit GHC state on it and check if the actual results match with the theoretically expected results. And the theoretically expected result will be what? 8 zeros or 8 ones, but nothing else. Like you cannot have 0001 or something like that. And actually, you will see that there is a deviation. You will sometimes actually get something like 0010 or something like that. And you have to think about why or why not that's the case. What makes a simulator different from a hardware?